Now in the another class of self-induction. So we will discuss self-induction. Self-induction is the property of a coil by virtue of which it opposes the growth or decay of current flowing through it. So think over this first. It is the property of the coil which opposes both growth and decay of the current. If the current is increasing, then that coil or coil's property, it opposes the flow of growth of the current. And if current decays, then we will see that coil opposes the decay of the current. It does not want to decrease the current in the coil. Self-induction is also known as inertia of electricity. I am going to show here one experiment. We will add here the one coil just like the solenoid, that is the inductor, and a resistance in parallel. And through this a bulb is connected. See this. What happens when this key is closed? This is the inductor denoted by L and this is the resistance denoted by R. So when key is closed, the current flows. We will see this element, this bulb B1, this is the bulb B2. It glows as we close the circuit, and we will see the first of all this B2, that we found that glow is increasing, means current flowing through this becomes lower to higher and higher, and ultimately it brights. And we will find here now in the bulb B1 the glowing is immediately start when key is closed, and in this one we will find the glowing is delayed. So this happens here now. Due to this inductor, it opposes the flow of current. Now here when it is opened, we will see it's put off quickly and it gets delayed. Now we are going to hear now coefficient of self-induction. Coefficient of self-induction. It is also known as self-inductance of that coil. So let current I flows through the coil at any instant. Definitely the magnetic flux linked with the coil is found to be proportional to the strength of the current. Means if current is higher, magnetic flux will be higher. So we can say that phi B magnetic flux, it is directly proportional to I current. So we can write here now phi B equals to a constant which is denoted by L I. So this L is known as self inductance. So L is the self inductance. So thus coefficient of self induction of a coil is defined as when value of I, this will be 1 ampere, then L becomes phi b. So here on the basis of this we can define the self induction as the magnetic flux linked with the coil when unit current flows through it. Now according to Faraday's law, we know here that EMF induced is equals to d phi by d phi b by dt, putting minus sign here. This is the Faraday's law. So this can be written as here minus d by dt and phi b, this equals to this. So we can write here, then this equals to minus d minus L d by dt I. This is here the induced EMF in a coil. Now suppose this minus di by dt, this is L minus di by dt. This portion, if minus di by dt is equals to 1, that means this L will be equals to epsilon, means self induction is equals to EMF produced in that coil. So on the basis of this we can also define the self induction as the induced EMF produced in the coil through which rate of decrease of current, this is unity. Second thing, I just want to say that its SI unit, it is very important. SI unit. SI unit is Henry. It is denoted by capital H. So we know here L, value of this formula is equals to L di by dt. From this we can say L equals to EMF by di by dt. So here from this we can say that 1 Henry is equals to EMF E 1 volt by di by dt, it is 1 ampere by 1 second. Now this will be equals to 1 volt per ampere second. So 1 Henry equals to 1 volt per ampere second. Then we know also L equals to phi by I from this formula. Phi equals to Li from this formula, it we also discussed. So from here 1 Henry is equals to phi, that can be expressed in Weber by I ampere, 1 ampere. This is equals to 1 Weber per ampere. So 1 Henry is equals to 1 Weber per ampere. So we can say 1 Henry equals to this and equals to this. So 1 Henry equals to 1 volt per ampere second equals to 1 Weber per ampere. So this is the very important thing. Another thing you know very well, 1 millihenry equals to 10 to the power minus 3 Henry. We can say 1 microhenry is equals to 10 to the power minus 6 Henry. So you have to learn these all for the calculations. Now one thing more, that inductor is generally represented, as I said you earlier, that like that here. This is the inductor and this is the resistance. So we should know here the difference between this and this. This is the inductor and this is the resistance. I think it is clear. Second thing, we are going to find out the self-inductance of a solenoid. Self-inductance of a solenoid. Solenoid, you can say that it is an inductor. So consider here a solenoid of length L. Its length is L. This is the solenoid of L length. And suppose I current is flowing through this. So consider here number of turns per unit length in this solenoid, that is N. Small n is the number of turns per unit length. So magnetic field inside this solenoid, that will be equals to B equals to mu naught Ni when it is kept in the vacuum, and total number of turns, it is denoted by N. This equals to N into L, where N is the number of turns per unit length and L is the length of the solenoid. So magnetic flux linked with each turn d phi by d phi b, this is the magnetic flux linked with one term. Definitely this will be equals to B into A. We know this here. So this equals to B, value of B, this is mu naught Ni, we have placed here. Now this area A. So this is here the magnetic flux linked with each turn. Now we are going to find out total magnetic flux linked with the whole solenoid. Suppose it is phi b. So phi b, that will be equals to this magnetic flux into number of turns. That will be here this mu naught Nia into number of turns NL. I think here is no problem. Then we can write this mu naught this N square, then here N square we can put I A L. This is here the magnetic flux linked with the whole solenoid. But we know here magnetic flux, that will be according from the definition, it will be Li. So we have here the equation number 1 and this is the equation number 2. If we compare these two, then we can write Li is equals to mu naught n square I A L. Then L equals to mu naught n square AL, cancelling these two I here. So we can say this is here the self-inductance of the solenoid. Second thing, we can write this equation in another way, like that mu square n here, from here we can write n equals to n by L. So this becomes n square by L square AL. Now here 1L may be cancelled, then this equals to mu naught n square A by L. This is here the relation. So we can say on the basis of this, self-inductance of air-cooled solenoid, that means in the solenoid, if it is kept in air or vacuum, then this L depends upon this number of turns. This also depends upon L, means L, if L increases, the inductance decreases. N increases, inductance increases. Area increases, inductance increases. And this also depends upon the nature of material of the core. Thank you.